So now we move on to the next speaker. Let me introduce our next speaker, Engineer Charles Chen. Engineer Charles Chen is a fellow of HKIE, IGEM, and IMAE. He has been practicing as a mechanical and gas engineer for over 40 years, with experience in fuel, gas, and other chemical process. Engineer Chen has been serving in committees of various engineering institutes, as well as on government consultative board. His experience covers a wide range of gas, including LPG, natural gas, biogas, industrial gas, and more recently, hydrogens. Ladies and gentlemen, please welcome our next speaker, Engineer Charles Chen.
Okay, thank you very much for giving me this opportunity to share with you. Right, the potential of using liquid hydrogen to power fuel cells, and specifically for mobile equipment like vehicles or aircrafts, like what the first speaker introduced this morning. Now, before we go into that topic, let's go back a little bit and talk about this thing here. Now, these are all electric vehicles, right? Now, for this one, right, or the one on the left, no doubt this is an electric vehicle, 電車, everyone knows that, right? Because it runs on electricity. Now, this form of transportation appeared more than 100 years ago. At that time, cities roll. People need some form of mass transit, and they need to pack a lot of people into one vehicle. And what's the best way to power that? Obviously, at that time, the best thing is for an electric motor, right? The problem is, where do we get the electric power from? Now, given the technology at that time, right, if they use battery, the only battery available was the lead-acid battery, which is not very the power to weight ratio is not very good. So if you use that, almost half the tram will be filled up with battery, and that's not very practical. So the only way to power that electric motor is actually to run the overhead cable and obtain your power from there. So that's the technology, that's the limitation, and that's the solution. Up on the top, we see a diesel electric locomotive. In the middle of the last century, people started to realize that steam, coal locomotives is not very efficient, though they go to electric. Now, the problem again is, where do we get the power from, right? Overhead cable over thousands of miles is not very practical. So the best thing is to put an electric generator right at the locomotive and give power from there. So with that level of technology available at that time, that's the best solution. Okay. In the middle, you see two buses. If you look close enough, actually, one is an electric bus, electric battery bus. The other one is a hydrogen bus, side by side. Well, actually, both of them are electric vehicles, right? Despite one is being called hydrogen bus, because that hydrogen bus actually runs on an electric motor. They just have different sources of electric supply. One is from battery, and the other one is from a hydrogen fuel cell. That's the only difference. Eventually, they all run on electric, right? Now, if you compare that with the tram, technology today has allowed a different form of powering the electric motor. They can use either a lithium battery, which is much more efficient than the lead-acid battery, and they have a choice of using hydrogen fuel cell. So today's technology actually offers more options for powering your electric motor, okay? Now, just as a point of interest, on the far right-hand side, you see a tank. There's actually a Tiger tank, which is a bit different from the Tiger tank, if you're a history buff, a bit different from the Tiger tank that you're used to, because at that time, Germany gave up a tender for 2 contenders to come up with a design. And this is the design that didn't succeed. This one was actually by Professor Ferdinand Porsche, the famous Dr. Porsche. He is a bit ahead of his time. Because this thing is so heavy, if you use an internal combustion engine, you need a very complex gearbox. And that's too heavy, too complicated. He had a smart idea. Why not use an electric motor? Because that eliminates the need for a gearbox. So this tank is actually powered by an onboard IC engine generator, generating electricity for the electric motor. So what you see on the lower photo is actually the two motors driving the two drive wheels. But given the technology available at that time, his idea is a bit too ahead of his time and wasn't quite a success, right? At least Mr. Hitler didn't buy the idea, so that didn't went into production. Now, why did I talk about that? Because we have seen that with changes in technology, we can have different options for powering the electric motor. Now, the same concept actually applies to our fuel cell, right? Actually, as we have seen from various speakers earlier, there are different forms of hydrogen storage available. Well, Dr. Leung just talked about liquid hydrogen, solid-state hydrogen, et cetera, right? Now, this is a table that shows the various forms available at the moment. On the top is obviously compressed gas, compressed hydrogen. And this is the most common prolific form of storage and transportation used right now because this is the most mature technology. The infrastructure is widely available because compressed gas we use every day, from oxyacetylene for welding, hydrogen and oxygen for medical use, right? We encounter compressed gas every day. So the infrastructure there is commonly available, no problem. Liquid hydrogen is less common, right? It's confined to certain areas. It has advantage over compressed hydrogen in that the energy density is much higher, more than 2 times, as you can see from the table. But the problem, one of the big problems is it needs a very low temperature, minus 253, right? We'll look more into that later. But it offers high energy density. That's the best thing, and that's why this is a very useful option. The other alternatives which we have talked about earlier today, metal halide solid state, liquid organic H2, all right, and absorption or ammonia, as Dr. Leung just talked about now. These are all other forms of storage, but they all have their own drawbacks. Either they're too heavy, they take up too much volume, they need energy for transferring back to hydrogen, etc., which makes them not quite suitable, especially for vehicle, which you have to move around, right? Too heavy, too much space, etc. So liquid hydrogen looks like probably the only other alternative that is available. Now, let's look at what is liquid hydrogen, right? We need to cool hydrogen down to minus 253 degrees in order to liquefy, okay? Now, how cold is that? That is 20 degrees, 20 K, which is only 20 degrees above absolute zero, very, very low, all right? This is not a new material. The world has been using liquid hydrogen for more than half a century, ever since Germany came up with the first rocket in 1944. And NASA and other space programs, including Chinese Shenzhou program, they all use liquid hydrogen, right? So it's not a new thing. People are familiar with it. Well, familiar in that they are confined to certain circles, not widely used in the industry, okay? Hydrogen, it has a very high specific energy, that is energy per mass. So 1 kilogram of hydrogen compared to 1 kilogram of gasoline, hydrogen contains much more energy. But the problem is, hydrogen is so light that volumetrically, it is not good at all. You need a lot of space to pack the same amount of energy, even in liquid form. Now, if you look at the requirements in the vehicle, right, there are a few main criteria. Number one, it has to be refilled quickly, right? The biggest drawback with a electric battery vehicle is it needs too much time for charging. It needs to be refilled quickly. The range needs to be about 500K, which people are normally used to with the petrol vehicles. And for sedan, right, to cover this range, you need about 4 to 6 kilograms of hydrogen. So the Toyota Mirai, it has 5.6 kilograms of hydrogen on board. If you use it on a long-haul truck, it has to cover a range of about 1,200 kilometers. And that would take around 65 kilograms of hydrogen in order to do that performance. Now, 5 to 6 kilograms of hydrogen for sedan, how much is that? With that density, that would occupy about 86 cubic meter. And that translates into a balloon, if you at NTP, that would be a balloon of about 5.5 meters in diameter. Now, obviously, this is not practical. You cannot, tow a balloon that big at the back of a car to power your car. So the only way now is to actually compress it, highly compressed, actually. All right. So you see all the trailers compressed to 250 bar. For truck, 350, and for sedan, because the space is more at a premium, you compress it even to 700 bars. All right. Now, how high is the pressure? The normal compressed gas we're talking about, all right, is industrial gas is about 200 bars, nitrogen, oxygen, etc., CO2, 200 bars. So 250 already is high pressure. 350, 700 is very, very high pressure. Compressed hydrogen, right? Probably there are basically 5 types of cylinders. Type 1 is the most basic, all steel. They need the steel to withstand the pressure, and because steel is heavy, this is the most heavy type of cylinder. Not good. The most advanced one is type 5. Type 5 is using composite material, carbon fiber, whatever. It can be much lighter. But even with type 4, right? Type 5 is not commonly available. It's too expensive, too advanced. People normally use up to type 4 cylinders. Now, if you look at the table, type 1 is no good at all. The hydrogen to overall weight is only 1 to 2%. So for every kilogram of cylinder, you can only carry 1 to 2 kilogram, 1.1 to 0.2 kilogram of hydrogen. Very inefficient. Even if you go up to the very expensive type 4, you're talking about only 5 to 7% of hydrogen in the whole weight. Not good at all. Now, if we go to liquid hydrogen, you can go up to 9%, which is a big improvement. Still not good, 9% only, but still it is a big improvement. And also because you don't have to separate into small cylinders because of hoop stress, right? For high pressure storage, it has to be confined to small diameter cylinders. But for liquid hydrogen, because there's no pressure involved, you can have bigger cylinders. So the space occupied is much less. So this is another plus. So that's why liquid hydrogen becomes attractive. Now, still we say liquid hydrogen is only 9% weight of hydrogen in the whole weight. Why is it so heavy since you have no pressure involved? Well, it's heavy because of all the insulation and also peripheral safety gears. So it's still heavy, although it's a bit better than compressed hydrogen. And the other thing, other than just what just mentioned about, is with okay, so liquid hydrogen, the energy density is much more than compressed, even compressed up to 700 bars. All right, it's liquid hydrogen per meter cube. You can pack 71 kilogram volumetrically. Whereas even if you compress to 700 bar, you're talking about 40 kilogram. Okay, so there's a big difference in the energy density per volume. Okay, And the other good thing is it does not require high pressurization. Now that not only translates to safety, it also translates into other aspect. On the right is a diagram of a hydrogen filling station. You can see that to serve just one hydrogen dispenser, right, you need the whole lot of gear at the back. Firstly, you need a storage. Then you need a compressor to compress it to very high pressure for filling to a secondary storage. And so you have the compressor to start with. And then because hydrogen has a inverse Joule-Thomson effect. That is, when it expands, it actually heats up. It doesn't cool down. So you have to pre-cool the hydrogen before you dispense it. So you need a big cooling unit. Okay? So all these things, the compressor, big compressor, the cooling unit, the primary storage, secondary storage, all these stuff to serve just one dispenser takes up a lot of space. With liquid hydrogen, all these will be gone. But the drawbacks is it is very cold. Now, very cold has some indication. We'll look at that a bit more later. It has ball of gas. Again, we'll look at this. All right? Liquefaction is energy intensive. Safety is a concern. And then compressed hydrogen is a well-known infrastructure, is very mature, whereas liquid hydrogen, you have to go into new areas. Now, liquefaction. We all know that to liquefy, you need energy for the latent heat. Now, hydrogen, other than just latent heat, 12 megajoule per kilogram, that involves a phase, the isomer change from this orthoisomer to para-isomer, and that involves even more energy. So that's 26 in total already. And then with losses, inefficiencies, in practical terms, you need 36 to 45 megajoules per kilogram to liquefy 1 kilogram of hydrogen. Whereas for 1 kilo of hydrogen, you only get 109 megajoules of energy. So if you look at pie chart, with liquid hydrogen, a third of that is wasted in the liquefaction process. Whereas for compression, you only lose this much, right? So this is one of the biggest drawbacks, one of them. The second drawback, well, we'll look at that later. This is the high sensor with hydrogen. Cryogenic, cold burns, highly flammable. Well, we all know hydrogen is flammable, but with liquid hydrogen, the other bad thing is it can form a shock-sensitive mixture. One good thing about hydrogen is it's so light that when it leaks, it goes up to the air quickly without forming any explosive vapor cloud, right? That's with hydrogen. But the liquid hydrogen is different. Because it's cold, it doesn't rise. It will probably stay low, and it will form explosive vapor cloud, right? So this is another hazard of liquid hydrogen. Now, ball of gas. Because it's so cold, right, -253, compared with the other cryogenic liquid that we are familiar with, LNG. LNG is -185. So it's in an entirely different regime of things, okay? Ball of gas is, insulation is never 100% perfect. Heat will seep in, and with heat, you will have vaporization. Vaporization build up pressure. If you don't let go of the pressure, then the vessel will burst. That's ball of gas. Hydrogen, typically, you are looking at 1% per day of ball of gas. Compared with LNG, normally, we can go down to 0.06 to 0.1% per day. So there's a huge difference there, okay? Now, this ball of gas, you can either let it go, right, or reuse it. If you let it go, it will create hazard, you lose money, etc., okay? Are we using liquid hydrogen for vehicles? Yes, we are. 10 years ago, right, BMW already has this hydrogen 7. 20 years ago, actually, right, 2005. This is not a production model. This is I think they only built 7 of these, and sent to celebrities for the trials. Wasn't quite successful. It was told that for this vehicle, this one runs on liquid hydrogen, feeding an internal combustion engine, not fuel cell. If you let this vehicle stand there idle for a week, all the hydrogen will vaporize, gone. Right? It's so bad. 20 years on, things have improved quite a bit. Toyota recently developed this GR Corolla H2, which runs on liquid hydrogen. We'll look at this in a bit more detail later. And Daimler and Hyzon also developing liquid hydrogen truck. Also used for aviation, and Dr. Leung already said already LH2 is, this Hydra is already transporting liquid hydrogen to Japan. Now this Toyota Child 2, the innovative way is, yes, boil-off gas is inevitable, but they try to reuse the boil-off gas, right? They recycle it either for combustion or for fuel cell to, this one incidentally runs on internal combustion engine, okay? They use the electricity generate to power fuel cell to drive the pump, okay? They reuse the hydrogen. But the problem is, when you reuse the hydrogen, it's only good when the car is running. If the car is not running, you still have a boil-off gas. How do you deal with that? Nobody knows. This is the Daimler hydrogen bus, right? It is being trialed out. It can run more than 1,000 kilometers on one single charge. And the production is planned for the second half of this decade, so it's coming on stream. In China, in Qingdao, there is a production liquid hydrogen cylinder available, at least on the website, okay? The challenges, mainly two major problems. One is the very low temperature, which carries on to boil-off gas, and that is to do with insulation. If we improve on insulation, you can reduce the boil-off gas. And there are researches going on, and the most advanced technology at this stage is the multi-layer insulation. They rely on reflective surfaces, reflective infrared, and also vacuum, right, for insulation, which is vacuum. Everyone knows is a very good insulator. And sometimes they use active cooling. That is, they have a small refrigerant plant to keep it cool, something like that. So this is an area where we need to face the challenge, all right? Yeah, these are the advanced insulation, vacuum technology, etc. The benefits we've seen: longer range, more compact size, less weight, which carries on, translate into more payloads. So this is good for especially the truck industry. So in conclusion, all right, liquid hydrogen has the potential, right, to improve the usage of hydrogen. But there are key challenges to overcome, which is insulation, boil-off gas, and also the high energy use for liquefaction. So we need to do more things there. And call to action is policy support, R&D investments. Okay, so that concludes my presentation. Thank you.
Oh, thank you, Engineer Charles Chen. Give us a fruitful talk